First, we are going to analyze the advection equation, or it's also called the wave equation. And this is as a particular case of a hyperbolic partial differential equation. As you can see here, it's a second order partial differential equation, linear, second order both in space and time. And here this c, it's a constant, and in the simplest case, it can be, of course, a function, any function of position and time as well. And this advection or wave equation, as any partial differential equation, is based on some principle. In this case, it's a physical principle that, for curiosity, I'm just mentioning here. Basically is based on the conservation of particles inside a volume. So basically, as the fluid is incompressible, basically means that it's based on the following: the number of particles going inside the volume should be equal to the number of particles going out of the volume, because the fluid is incompressible. And applying that principle, this equation can be derived in order that principle to be applied. And very interesting idea, that equation can be separated in these two equations, can be written in this way. And so in order that to be zero, you can have that either this one is zero, or you can have that this one, the other one, is zero. And actually you can have that actually both equations are pretty much the same. The only difference is the sign that we do have here. Actually, we are going to center our analysis on this equation here, but actually the features of the other equation can be easily derived from this equation as well. So that's why here I'm just going to present the advection or the wave equation that we are going to analyze in detail in order to characterize different numerical methods in order to solve that equation. And as we have said, we are going to center our analysis on this equation here. And actually, the simplest version of this equation, where this c constant, it's a constant, it has a quite easy analytical solution. And the analytical solution is the following. Just consider that that we do have as initial condition that the wave, the u function, has some form. Let's say this is the initial condition. If this is the initial condition where the wave function has this form, let's suppose that this is the form that we have for initially for the wave. So that's what this is, the representation for the wave initially. Then we have that from here we can easily derive that the expression for the wave at any time, so the u function at any time, it's just this one is the u naught, but instead of x we have to write here x plus ct. So this is the x and t dependence that the wave function would have at any time. And basically it means that the form at any time of the function is going to be the same as the one you do have initially. The only thing is that it's displaced, in this case, to the left. It's displaced to the left. But the form, more or less I have done it here, so the form of the orange and the blue functions are going to be different. The only thing here is that the u function evaluated at any time, so that would be the u function evaluated at any time as a function of x, it's basically displaced by c times t. So the displacement at any time will be c, which is this constant, times t. So that's as we can see here, it's easy to see once we know the initial shape of the wave. It's easy to derive how the wave is going to look like at any time. And once we do know now, of course, this is just in the case that this c parameter here is a constant. If this c parameter depends on position and time, then we cannot say that, and the analytical evaluation of this equation can become strongly complicated. So, but when c is constant, the analytic solutions, you can see it's pretty easy, and that's going to be useful for us in order to check the validity of different numerical methods that we are going to apply for this advection equation, and we are going to analyze in the next sections.